Hey everyone, this is Mr. Vo, and I'm here to talk about EQ3 for topic 3. How can the behavior of gases be predicted under changing conditions, right? So we're looking at how gases will behave when either the pressure or the volume, the temperature or the amount of gases are different, right? So these are more like real life applications for gases that you've been learning about the gas laws. So wonder if this has ever happened to you, right? You haven't ridden your bike in a long time, and all of a sudden you see that you have a flat tire. So what's been going on? Okay. So it's not that there's anything wrong with it, but it's that your tires aren't completely solid, if you're ever surprised about that. And the reason why is because, despite how solid something is, there's always an opening, right? And so tires have tiny little openings in them that lets air, which is much smaller than the tire is, escape. Not quickly, but just slowly over time. Okay, so that's what we call effusion, the opening or the escaping of gases through small openings. Okay, this is different than what we call diffusion or effusion, right? And we're still talking about effusion right now, right? They have to be really, really small. So even if you have a lot of molecules moving randomly, right, eventually one will escape in a container, right? So this is the main reason why helium, which is very light and smaller, diffuses faster than oxygen, right? So if you pump up a helium balloon, helium at this point, weighs 4 grams per mole, right? While oxygen, which is O2, weighs 32 grams per mole, right? So helium is much, much, much smaller than oxygen is. And so helium will escape faster, okay? What other gas is also a very light gas, guys? It is called hydrogen. It's a pretty light gas, much lighter than helium is. So diffusion is different than effusion because you're moving from areas of high concentration to areas of lower concentration, right? This is just the movement of gas particles where there's a lot of it to where there is less of it, right? That's not the best definition, but or example, but you're moving from where there's a lot of it to where there is little. High concentration to low concentration for gases, right? So this is also the same idea, is that the lighter the gas particle is, right, the faster it moves, okay? So other things that we wanted to talk about include changes, right? When we're talking about changes in volume, changes in temperature, the amount of gas, we call this now moles, right? And pressure. Those are what will affect how gases will behave, whether or not they will move the particles much faster or not. So when you're looking at the relationship among the gas variables, right, you look at how they will change. So pressure, temperature, and volume, right, are going to be, imagine that's balanced on a pencil, right? If you hold the pencil by the T area, right? So if I change pressure, pressure goes down, volume goes up, okay? If I change temperature and volume, right, then they will go down or up at the same time. Those are called direct relationships, right? So pressure and volume are what we call inverse relationships, pressure and volume, okay? So that's what's going to change if I move one, the opposite side of the other side, okay? Same side, of course, opposite sides, okay? That might help you when you're solving for these following problems. If you hold the pencil by the V eraser, right? If one changes temperature or pressure, right, it's going to, it will adjust accordingly, right? So temperature and volume are directly related, or if I have volume constant, temperature and pressure are related as well, okay? All right, so here is one instance, right? When one of the variables of a gas is changed, it can affect the other variables in predictable ways. So if the pressure and temperature of a gas are kept constant, what will happen to the volume of the gas when more particles are added? So here you can see that there are more particles that exist. This is a little bit more and much more. So volume, right, and pressure are inversely related, right? So the increased volume. So with more moles present, more gases, the volume will increase, okay? The volume will increase. All right, what will you do to the volume of a gas to reduce its pressure to 1/4 of the original value, keeping the temperature constant? Okay, so my goal is to reduce the pressure, okay? So remember that pencil, you have, what we do to the volume of gas to reduce its pressure to 1/4. So in order for the pressure and volume are inversely related, so if I want to reduce the pressure, volume will have to increase. So anyone here where it says the volume will have to increase, right over here, yeah, it says the volume will have to decrease. No, doing nothing doesn't change the behavior. So the only answer you can have is to increase the volume 4 times, making something much, much bigger. So the pressure is lower, okay? All right, keeping the pressure constant, how would you increase the pressure in the gas by keeping the temperature constant? How would you increase the pressure by 100-fold? Okay, so remember pressure and volume are inversely related, right? So if I want to increase the pressure, I need to decrease the volume. Okay, if I want to increase the pressure, I need to decrease the volume. That's the idea of an inverse relationship. So that I would have to do this one. Okay, and then it says keeping the temperature constant. So here I can't do that. I can't heat up the gas to 100 times the original Fahrenheit temperature. Okay, another one is if I want to increase the pressure, adding more things in it is going to also increase the pressure as well. Okay, so there's two options to this: decreasing the volume and increasing the number of particles in there. So when we look at pressure, right, the idea is which one, if you look among between these two, right, how do you know that why can a person who weighs 150 pounds exert more pressure? And it's all about that, right? Those heels, right? An elephant is able to exert the same amount of pressure as someone in heels because even though it weighs more, it is more spread out. Okay, this one, the pressure is all on a few spots on the heel. So that's going to be something to think about, okay? So again, pressure is force per unit area. So depends on how much area it takes, or the surface area it takes, that's how much pressure there's going to be. So how do you know if you have different situations with high pressure? Take a look at this. You have a sharp knife, right? Sharp knives don't need that much surface area, but if you're pressing on that thing, right? So know that a knife is really thin at the edges, okay? So lots of pressure can can be placed on that. Pins are the same thing. You don't need much, you don't want to have much surface area for a pin, and it can definitely penetrate through things much quickly. Same thing with soccer boots or soccer cleats, right? They don't have much contact with the ground. It helps you push yourself off, which helps you run faster in poor terrain. Okay, so that's why high pressure is so important. Now, sometimes when you want the opposite effect, right? Like if you want to relieve pressure, right? Lots of people wearing backpacks right now, rather than carrying a things just by hand, you want to distribute the weight. So the shoulder pads are sometimes they have to be wider so that they're more comfortable. More often than not, you have a backpack with two straps because you want to distribute the weight and the surface area among both of your shoulders. Okay. Skiing is something else, right? Like you want to reduce that pressure so that you can stay above the snow. Okay. Tractors also have wide tires so that they don't sink to the ground due to high pressure. So atmospheric pressure is that pressure one feels, right, when you are standing at zero at zero altitude at sea level. Okay, so you basically feel 14.7 pounds for every square inch of your body, right? And so your goal is to understand that you're always under some pressure. You're just used to it. Okay. So as you get below sea level, you're going to feel changes, right? Below sea level, there is more pressure, and then as you reach higher, there's less atmosphere, right? And so there are fewer collisions. Fewer collisions means lower pressure. Okay. So you have the higher you get, the less pressure there is. Okay, so the changes in sea level, right? You have at 5,600 meters above sea level, the atmospheric pressure is about 50,000 PA, or 5 times 10 to the fourth PA, right? And so how much of a difference is that then the pressure one feels, right? It's almost like more than a magnitude of difference, 10 times the difference in pressure at 5,600 meters above sea level versus at sea level, okay? So you have more pressure the lower to the atmosphere, the lower to the surface of the earth you get. So boiling points change, right? So when there is less atmospheric pressure, the boiling point is lowered, and then boiling point is low. So you really got to cook food much longer, right? Because with a low boiling point, some things might not cook uh, like that at the same amount of time as you would at near sea level. Okay. So the reasoning, the lower atmosphere means there's fewer particles pressing against the water. Okay. So if we're cooking rice in South Lake Tahoe, how does it compare to cooking rice in San Jose? It will definitely take more time. Okay. It will definitely take more time, even though the boiling point is a little bit lower. Okay. When you're breathing underwater, that is also going to affect the number of feet below seawater. Okay. The main reason why is that the deeper you go, the more pressure there is, right? You want to have some equilibrium. That means your pressure internally needs to match the pressure outside. So with more pressure outside, it's going to be much, much harder to breathe. Okay. So the problem is you don't want to mix that air, the high pressured air with the low pressured air, right? And so that's why people have a gas tube um, that connects them to the oxygen so that they can have reached equilibrium. Okay, so high pressure in gas means that more gas particles are present in the lungs, and those will dissolve in the bloodstream. So you don't want to have gas dissolved in your bloodstream when you are going deep sea diving. Okay, so the name of this medical condition that arises from the presence of gas bubbles is called the bends. Okay, and again, that's going to keep you from feeling too comfortable. Sometimes it can kill you. And that's it. We will talk about the rest of, well, I'm just going to stop there.